All right, now for a look at the Argand diagram. Jean-Robert Argand, a French mathematician, I don't know, around in the 1600s. He came up with this idea of representing a complex number on a two-dimensional plane. So Gauss is also credited with some work here. So it's also known as, I suppose we could say, aka it's the Gaussian. Although I don't think I'll refer to it as the Gaussian plane, I don't tend to. The Gaussian plane, or somewhat more dryly as the complex plane. I would only talk about it as the complex plane, probably in the initial stages, while we sort of get used to the idea that the Argand diagram is dealing with complex numbers. So, but I'm going to call it the Argand diagram, and I encourage you to as well. Okay, so let's have a look. It's a pretty simple idea. We're going to we're going to represent this complex number z, which we have already been introduced to as in general form, a plus ib. So that's going to be a point here on our plane that matches up with our imaginary axis, which is our vertical axis, and our real axis, which is our horizontal axis. Okay, so that is our a plus ib, so we're going to move a along the real axis. This is my real element of z, and this is my imaginary element of z, and so we're going up to b in the imaginary number a plus ib. So that's there it is there. That's the complex number represented on the Argand diagram. Not a terribly difficult concept, is it? But it's one that we're gonna. It's a very visual area, actually, complex numbers, and so this is, I guess, an important, very straightforward but very important idea, and no doubt it will become more complex, pardon the pun, as we move into it. So the Argand diagram, there it is. So what do we need to know about it? Not much, other than that's how we represent the number on it. I'm going to bring into the vocab now, or into our bag of tricks. We're going to look at the modulus, which is just the distance. So the modulus of z, modulus of my complex number. All right, now that is the distance. The distance of my complex number z, all right, as represented. So this is where, without the Argand diagram, it doesn't really make sense to talk about the modulus of z. The distance as represented on the Argand diagram, from the origin. So the distance of the point, the complex number, on the Argand diagram from the origin. So that is this distance right here. So if we join the origin to our complex number, right, it's that distance there. Okay, so that is I'm just going to underline this as well. The modulus of z is the distance of point z as represented on the Argand diagram from the origin. So we denote it as, we use our modulus, or our absolute value symbol for this. So we say that this is the modulus of z, that distance there from the origin to the point. Okay, so what is that distance? Well, we've got a nice little right angled triangle here, don't we? Where our shorter sides are a and b. So we will say, therefore, that the modulus of z, right, that's what that says. That says, right, the modulus of z, which just means the length of z when connected to the origin. Well, that's going to equal the absolute value the absolute value, square root of a squared plus b squared, remembering that that a and b are our coefficients, a being the real part and b being the imaginary part of z. Okay, so let's do a couple of examples, and before we go and do question 2 from 3F, so some examples. All right, in part A here we have z equaling 5 minus 12i. That's my complex number. I want to find the modulus of it, so I might, for this example, we might just have a little look at it. All right, 5 minus 12i, so 5 on my real axis, 3, 4, 5. I don't know why I'm trying to do this, because minus 12 is going to be way down here somewhere. Right, so my modulus is going to be that distance there, where I have a right angle triangle, 5 here and 12 here. So I don't need to do this each time, I'm just doing it out of demonstration. I know that my modulus therefore of z, but I do want you to write this out please, is equal to 5 squared plus 12 squared, which is equal to the square root of 25 plus 144, which is 169. So z will be equal to 13. That's my modulus of z. So go ahead and do B and C if you wish, and pop back and see if we agree. So in B, z is equal to 1/2 minus 1/4 I. Now you'll notice there I'm splitting my coefficient from my I. I want to see what my A and B are, because my modulus of z is going to call on those values. So I've got the square root of 1/2 squared plus, I'll put the negative 1/4 squared in there, but we know it's just the same as 1/4 squared. So I've got the square root of 1/4 plus 1/16. So if I put these together, I've got 4/16 plus 1/16, which is 5/16. Or if I split my surd up, it's the square root of 5/4. There's no negative value here. My modulus is always positive. I'm finding a distance. I'm finding a length. And C. I've got z is equal to, now I want to see again, I want to have a look at minus 21/29, my real part, plus 20/29 I. I'm interested in my values of A and B. So in I go with my Pythagoras work. I'm going to have negative 21/29 squared plus 20/29 squared. Okay, so this is going to be quite big. Okay, so I just got the calculator out for this. 21 squared is 441, so I'm going to have 441 here over 29 squared, which is 841. And 20 squared is 400. I don't know what right equals there. That's a plus. 20 squared is 400. 29 squared, 841. Let's put those together. Looks like I've got, very conveniently, 841 over 841. So my modulus is just 1. Now, exercise 3, what are we on? 3F. And let's go to question 2, please. Just question 2, then pop back for the next video for question 3. Okay, so let's now go and do exercise 3F and complete question 2. There'll be a third video for question 3, so come back for that.